let's talk about integration by parts. I need to get a good color here. There we go. Integration by parts. This is the closest that we'll ever have to a product rule for integrals. We don't have a product rule. This is not a product rule, but this is similar to the product rule. Integration by parts uses the product rule of derivatives to help us break integrals into simpler pieces. Keep in mind that if we're taking the derivative of a product, u times v, this is u times v prime plus u prime times v. So we're going to use this idea and we're kind of going to go backwards on it. So we're going to do the integral of this. So now the integral of uv dx is u times the integral of v minus the integral of the derivative of u times the integral of v dx. All right, du is the derivative of the u function, iv is the antiderivative of the v function, and we always take the simplest antiderivative where c is equal to 0. Always just use c equals 0 until the very end of the problem. Okay, so now we have this table method that we could do. The sign always alternates, positive, negative, positive, and at some point around the way we'll have this integral again. Here's what we do. Evaluate the integral using integration by parts where possible. Use the tabular method. So we have the sign, we have the derivative, and we have the integral. Now we're looking at our integrand, and we're asking ourselves 3x minus 1 times e to the negative x. Which one is easier to find a derivative, and which one's easier to find an integral? In this case, that 3x minus 1 is super easy to find the derivative, and because it's a polynomial, we know the derivative eventually goes to 0. So this is 3x minus 1. We could take the derivative and get 3. Take the derivative of 3 and get 0. Now that we took the derivative all the way down to 0, we take the integral. What's the integral? The first piece is e to the negative x. The antiderivative is negative e to the negative x. If you need to, do that over here with a simple little u substitution. du is negative 1 dx. We'll take that negative 1 to the other side. Now we have negative integral of e to the u du, and that's how we get our negative e to the negative x. All right, do the integral again, and a negative makes a positive. That's why we like this integral. This integral is an easy one to find because it's a simple, not easy, but simple u substitution. So I find the integral for the same number of levels, and then here's how it goes. The integral of 3x minus 1 e to the negative x dx. We take this first derivative, right, the u as it originally was, 3x minus 1, multiply by the integral of e to the negative x, so minus e to the minus x. And then the next sign is minus. We'll take 3 times e to the negative x plus c. Because I have a 0 here, it turns out we've already done the derivative times the integral. We've already integrated that. We can just write this off as a negative 3x. Here's a positive 1 and a negative 3, which makes a negative 2, all times e to the negative x plus c. All right. Now, sometimes we have to go several steps. The sign is always going to alternate, starting with plus, minus, plus, minus. I choose which piece for my derivative, 1 minus x squared, easier to find the derivative of. Exponential function, easier to find an antiderivative of. So 1 minus x squared, I write it in my table. I take the derivative, I'll get minus 2x. I'll take the derivative of that, get minus 2. The derivative of that, I'll get 0. So I know I need 4 levels. That's how I know I go plus, plus, and then minus has the integral always. When we're dealing with polynomials as my derivative column, we never have to find an integral again because it always just kind of reads off here as we go along. All right. If the derivative part is 1 minus x squared, the integral part is 2 to the negative x. Find its antiderivative. Remember, the antiderivative of a to the x dx, let's say this correctly, is a to the x over the natural log of a. All right, in this case, it's a negative x, so just like we had to use a u substitution up here, we'll alternate negative, positive, negative in the sign. Divide by the natural log of 2, take the derivative again, we'll have natural log of 2 squared in the denominator. Excuse me, take the antiderivative again, we'll have natural log of 2 in the cubed in the denominator. Right, first antiderivative, we have natural log of 2. Second antiderivative, we'll have natural log of 2 squared in the denominator, third antiderivative, so on. So when we put these together, we start with the derivative and we step down 1. So the positive, 1 minus x squared times a negative 2 to the negative x over natural log of 2. And then a minus sign, minus 2x times 2 to the negative x natural log of 2 squared. And then a plus sign, negative 2 times negative 2 to the negative x over natural log of 2 cubed, minus the integral of 0 times, and as soon as we say 0 times, we're happy because 0 multiplied by anything other than infinity is 0. And don't forget the plus c. So this is just reading it off from the table, but that's horribly ugly. What I'm going to do instead is just tighten it up, write it a little easier to read. So we'll put the negative and the 1 minus x squared over the natural log of 2 and have my exponential function 2 to the negative x behind. Two negatives make a positive. I'll have 2x over the natural log of 2 squared times 2 to the negative x. Here, a plus a negative. Oh, and there's another negative, so I have two negatives, keeps that positive. 2 over the natural log of 2 cubed times 2 to the negative x plus c. If I wanted to, I could write this as 2 to the negative x and then times, multiply by all of this. I could take out a natural log of 2 even, but it's not necessary. Right? That's a fine answer as it is. All right. If one of the factors in the integrand is a polynomial and the other factor is a function that can be integrated repeatedly, put the polynomial in the D column and keep differentiating until you get 0. Then complete the I column to the same depth and read off the answer. And that's what we did in that previous problem. But you see, now we have a problem because we don't know what the integral of the natural log of t is. We have no idea, but we know that the derivative of the natural log of t is just 1 over t. So we always put the natural log, or a log of any type, in the derivative column because we can find the derivative, we cannot find the integral. So I'll put natural log of t and I'll find its derivative 1 over t. This is never going to stop, right? It's not a polynomial, so I'm just going to do 2 steps. I'll take t to the 1/3 and I'll take its integral, its antiderivative. So I have t to the 1/3 plus 1 divided by 1/3 plus 1. 1/3 plus 1, that's 1/3 plus 3/3. That's how I get 4/3. And remember, if we're dividing by 4/3, we're multiplying by the reciprocal, which is 3/4. All right. So now we have the derivative in 2 steps, the integral in 2 steps. These are the only 2 steps we can really guarantee. Always a plus and then a minus of the integral. So I can rewrite my integral of t to the 1/3 natural log of t dt as the natural log of t times 3/4 t to the 4/3 minus the integral of 1 over t times 3t to the 4/3 over 4. All right, so we have u I of v minus the integral of du I v and d, whatever our variable is here. Okay, nothing we can do with this first thing. It is what it is. We'll leave it here. Let's simplify here, however. The 3/4, that's going to be our coefficient. T to the 4/3 divided by t, right? Now I'm just subtracting 1, so 4/3 minus 1 takes me back to a t to the 1/3. And check it out. This 3/4 hangs out, right? Nothing we can do here still. Still have the minus sign. 3/4 hangs out. It's just a constant. We've already found the integral of t to the 1/3. We found the integral of t to the 1/3 over here, so we already know this answer. It's beautiful, right? We already have done this, so we're not finding anything new at this step. It's just we're using it again. So we have that 3t to the 4/3 over 4, and we can factor out the 3/4 t to the 4/3. We're left with the natural log of t minus 3/4. And don't forget your plus c. Okay, what about a definite integral? All right, the definite integral, as we talked about in 3.4, the fundamental theorem of calculus. We're still going to use the idea of partials. We're going to take a derivative piece, and we're going to take an integral piece. We almost always use an exponential for our integral piece. We always try to use a polynomial or a natural log or any type of log for our derivative piece. Since it is a polynomial, x squared plus x, we could take the derivative, 2x plus 1, take the derivative again, 2, take the derivative again, 0, and we know we have an end location. We can do the integral of e to the negative x. We did that earlier. That's negative e to the negative x, and then e to the negative x, and then negative e to the negative x. All right, just like we did on that earlier problem. I believe it was an earlier number 2. Could have been a number 1. All right, so we read it off as x squared plus x times a negative e to the negative x minus 2x plus 1 times e to the negative x plus 2 times a negative e to the negative x. Okay, so plus 2 times negative e to the negative x plus 0. But remember, we're not adding plus c here. Now we're evaluating from negative 1 to positive 1. So the first thing I'm going to do is put positive 1 in. And when I put positive 1 in where I have a negative x, it looks like a negative 1. So I'll have negative e to the negative 1 times 1 squared plus 1 minus e to the negative 1 times 2 to the 1, 2 times 1 plus 1 minus e to the negative 1 times 2. All right. Close those parentheses. Now subtract what we get when we substitute negative 1. Notice when I put negative 1 in for negative x, the exponents are positive 1s. Things change a little bit in the parentheses. Let's see how. 1 and 1 makes 2, so I have a minus 2 e to the negative 1. 2 plus 1 makes 3, so I have a minus 3 e to the negative 1. And a minus 2 e to the negative 1. Here we have negative 1 squared is 1. 1 plus a negative 1 is 0, so this cancels out. Negative 2 plus 1 is a negative 1. A negative 1 times a negative e makes a positive e. Right? The two negatives here. We'd still have the negative out in front. And here we have a minus 2e. So when I collect all these, 3, 4, 5, 6, 7, minus 7e to the negative 1, minus a negative e to the first power. Two negatives make a positive e minus 7 over e. Right? I took this negative 1 and put it down here. If it makes you feel better to put a 1 as an exponent on the e because your calculator always wants you to, I get it. You can, but it's not necessary. Yes, this is a nice exact answer. If your homework doesn't ask you for a decimal approximation, stop there. You don't need a calculator. Brains are better. Okay. Last example of integration by parts. Find the area bounded by the curve y equals x natural log of x. So that's our curve right here. It continues. It actually it doesn't. It starts right there. It continues up in this direction. The x-axis, right? X-axis, the lines x equals 1 and x equals e. All right, so this yellow region is the area that we're trying to find. X values are bounded by 1 and e, so my integral goes from 1 to e of my function x natural log of x dx. In order to find this antiderivative, because it has a natural log of x involved, we will use our tabular method. So we'll put the natural log of x here as our derivative line, and we'll take x as our integrals. Derivative of the natural log of x is 1 over x. Antiderivative of x is x squared over 2. So when I put these together, I will have natural log of x times x squared over 2, evaluated from 1 to e, minus the integral from 1 to e of 1 over x times x squared over 2. dx. Now I'm just going to rewrite this for right now. I'm not ready to evaluate it. I'll evaluate them all together. Let's simplify here. I'll have a minus. I have a 1/2. X squared divided by x leaves me with an x. What's the antiderivative of x? Remember, x over 2 is the same as 1/2 times x. Antiderivative of x is x squared over 2. If I already have a 1/2 in front, my over 2 gets multiplied by the 1/2, and I'll end up with 1/4. Evaluated from 1 to e as well. So what I did is evaluate both of these at e. E squared over 2 times natural log of e. Oh, I didn't. Minus. Okay, so I actually evaluated them separately. Minus 1 squared over 2 natural log of 1. Now, the natural log of e is 1, so I just get e squared over 2. The natural log of 1 is 0, so that part cancels out entirely. Minus sign. Now I'll evaluate 1/4 x squared at e. I'll get 1/4 e squared. And I'll evaluate it 1, so that's minus 1/4 times 1. When I have 1/2 e squared minus 1/4 e squared plus 1/4, I can factor a 1/4 out of, actually, I'm combining these two first. What's a half minus a quarter? That's 1/4 e squared plus the 1/4, and that's why I can factor out a 1/4, and I'm left with e squared plus the 1 that the 1/4 is multiplied by. Integration by parts using the tabular method. If you could take derivatives, which I know you can do, and if you could take integrals, antiderivatives, which I know you can do, you could do integration by parts and do more difficult problems as well. Thanks for listening. Remember, nope, I can't say that out loud in case I use this in a different semester. Enjoy.